Okay, here is another example of how we can calculate series parallel reluctance. You can see by the right hand side there is a core, but the core consists of two different parts. Of course, the L1, L2 is given by the size of the core, everything is different, is a toroid, correct? Okay. You can see by here from this point to this point is L1, and from this point, which is the new part, to the other side is L2. So L1 and L2 is given. So how we calculate the reluctance? We just go back to this formula. Reluctance is 1 over mu L over A. So if you look at the circuit very carefully, okay, you can see whatever the lengths different, okay, the cross-sectional also different, and these two reluctance connected in series, correct? So R1, reluctance number one, which is related to L1, is 1 over mu 0 times mu r, maybe two different material connected to each other, times L1 over A1. So I fully consider everything may happen to the circuit, okay? And R2 in the same way, just 1 over, so this is mu R1, mu 0, mu R2, if it's two different material, if the material the same, so okay, no problem. But L2 and A2, of course, you can see as a visualize is very clear, two different values here. Then R1 as a series connection plus R2 are equal, correct? Then assume we know MMF. If we know MMF here, means the value of MMF given as a N times I, okay? Can we calculate the flux density? Yes. The flux density value is MMF R phi, correct? So we know R, which R we should use? This R is the total R equal, okay? The phi is the value circulating whole circuit around here and there, from here to there. So the phi is the total phi. If we have two reluctance, is the phi different from each other when we are in the series connection? The current change? No. The current will be the same. So this is one of the example we can represent the value. Okay. Now we cover all of this in the same way. No worries. Yep, correct. Okay. Another circuit, case 2. We have case 2. Okay. Let's consider the case 2. In the case 2, we have the same, but here we have an air gap. Here we have an air gap. So how we can calculate the reluctance here? So we know the reluctance number one. We know the formula of the reluctance 1 over mu, which is mu 0 times mu r, correct? Times L, which L is the core length from here to here, which is L1, is shown by L1, correct? Divided by A, which is cross-sectional. So you can see the cross-sectional for both section the same, okay? One is, as you can see, I'm trying to make it filled by the cyan, cyan. Okay, no, this is R1, R2, which is for the air gap, is 1 over mu 0 for sure, because there is no other material there, times, what is L? L is L2, or For simply, we can call it LG. L, length of air gap. G is for gap, as you can see, air gap. Okay, divided by A. This A and this A are exactly identical, the same. Okay, shouldn't be the same, but here we assume to be the same. Later I will explain why they shouldn't be the same. Okay, but here we mention they are the same. Again, these two reluctance connected in series. So here simplified and make it simple for this case. For the next session, I will go through the magnetic circuit and Kirchhoff's law. I think it's the best to leave this one to review for the next session, and then going to Kirchhoff's law. Thank you very much for your attention.